Imagine traveling to a distant galaxy, light years away. It seems impossible, right? But what if there were shortcuts, cosmic tunnels that connect distant parts of the universe? These tunnels, my friends, are called wormholes. Wormholes are theoretical objects. They emerge from the equations of Einstein's theory of general relativity. This theory describes gravity as the curvature of space and time. Massive objects bend the fabric of space-time. This bending creates what we experience as gravity. Now imagine bending space-time so much that two distant points touch. That's the basic idea behind a wormhole. It's like poking a hole through a folded piece of paper. You create a shortcut between two points that are otherwise far apart. While wormholes are fascinating, we haven't observed them directly. They remain theoretical constructs, but the math says they could exist, and that's where the real excitement begins. The earliest type of wormhole we imagined was the Einstein-Rosen Bridge, named after, you guessed it, Albert Einstein and his colleague Nathan Rosen. They explored these ideas in the 1930s. Einstein-Rosen bridges are essentially tunnels through space-time. They connect two different points in the universe, potentially billions of light-years apart. Imagine jumping into one end and emerging on the other side in a completely different galaxy. But there's a catch. Einstein-Rosen bridges are thought to be incredibly unstable. They would likely collapse faster than the speed of light. This makes them impassable, even for a beam of light. So, while intriguing, they don't seem like practical interstellar highways. However, physicists haven't given up on the idea of traversable wormholes. These hypothetical wormholes would need some extra ingredients to stay open long enough for travel. And that's where things get even more mind-boggling. The idea of traversing a wormhole is tantalizing. Imagine the possibilities: journeys to distant stars and galaxies, perhaps even time travel itself. But could we ever hope to build or even find a wormhole that's stable enough for travel? The answer, like most things in theoretical physics, is a resounding maybe. You see, traversable wormholes, as we envision them, would require a special ingredient: exotic matter. Exotic matter is a hypothetical type of matter with negative mass. That's right, negative mass. Unlike everything we know and love in the universe, which has positive mass and attracts other matter through gravity, exotic matter would have the opposite effect. It would repel matter and potentially create a repulsive force to hold a wormhole open. The problem is, we've never observed exotic matter. It's purely theoretical. Some physicists believe it might exist in the quantum realm, but that's a story for another time. For now, the existence of traversable wormholes hinges on this elusive and enigmatic substance. Visualizing wormholes can be tricky. They involve bending and warping the very fabric of space and time, concepts that are hard to wrap our heads around. But there's a simple analogy that can help: folding a piece of paper. Imagine a piece of paper representing the vast expanse of space-time. Now draw two dots on opposite ends of the paper. These dots represent two distant points in the universe. To travel between them conventionally, you'd have to traverse the entire length of the paper. But what if you could fold the paper in half, bringing the two dots close together? That's essentially what a wormhole does. It folds space-time, creating a shortcut between two points that are otherwise light-years apart. Of course, this is a simplified analogy. Space-time is not a two-dimensional sheet of paper. It's a four-dimensional fabric woven from space and time. But the basic principle holds: wormholes warp this fabric, creating tunnels that connect distant regions. Section 5. Exotic matter. The fuel for wormholes. Traversable wormholes would require exotic matter. But what is this strange substance, and why is it crucial? Exotic matter has negative mass. It behaves in ways that defy our everyday experience. While positive mass attracts, exotic matter repels. This repulsive force holds a wormhole open. Wormholes are inherently unstable. They collapse faster than light. Exotic matter's repulsive gravity could counteract this, like air pressure in a balloon. The problem is, we've never found exotic matter. It remains a theoretical concept, a dream. Section 6. The instability problem: collapsing before we can enter. Even if we could somehow find or create exotic matter, stabilizing a wormhole wouldn't be easy. Wormholes are notoriously unstable. They're like delicate soap bubbles, prone to bursting at the slightest disturbance. The immense gravitational forces at play within a wormhole would constantly try to pull it closed. Even the tiniest perturbation, such as a spaceship trying to enter, could be enough to trigger a catastrophic collapse. Imagine a tunnel dug through a mountain. The weight of the mountain above constantly threatens to cave in the tunnel. Similarly, the fabric of space-time itself wants to collapse a wormhole. To counteract this instability, we'd need a tremendous amount of exotic matter, precisely distributed to create a stable throat through the wormhole. The slightest miscalculation could spell disaster, leading to a collapse faster than the speed of light. So even if exotic matter exists, engineering a stable wormhole would be a monumental task, requiring a level of precision and control over gravity that's far beyond our current capabilities. Wormholes and time travel. A recipe for paradoxes. The possibility of time travel is perhaps the most tantalizing aspect of wormhole physics. Could we bend time itself and journey to the past or future? Some physicists believe wormholes could act as time machines. By manipulating gravitational fields, we might create a time difference. Entering one end could transport us to the past or future, but time travel is fraught with paradoxes. The most famous is the grandfather paradox. Would you cease to exist, creating a logical inconsistency? These paradoxes highlight the complexities of time travel. Section 8. Quantum entanglement and wormholes. A mysterious connection. Quantum entanglement, one of the strangest phenomena in the quantum world, might hold a surprising connection to wormholes. Entanglement occurs when two particles become linked, even across vast distances. Measuring the state of one particle instantly determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, has puzzled physicists for decades. But some recent theories suggest that entanglement might be the key to understanding the nature of space-time itself. One intriguing idea is that entangled particles might be connected by microscopic wormholes. These quantum wormholes would be far too small to observe directly, but could provide the invisible threads that weave the fabric of space-time. If true, this connection between entanglement and wormholes could revolutionize our understanding of both quantum mechanics and general relativity. It could be the missing link between these two pillars of modern physics, potentially leading to a unified theory of quantum gravity. Section 9. ER EPR, a bridge between relativity and quantum mechanics. The ER EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, connects entanglement and wormholes. It suggests these phenomena are two sides of the same coin. ER stands for Einstein-Rosen Bridges, or wormholes. EPR refers to Einstein, Podolsky, and Rosen, who described quantum entanglement. The conjecture proposes every entangled pair is connected by a microscopic wormhole. If true, ER EPR could bridge general relativity and quantum mechanics. Section 10. The search for wormholes' current status and future prospects. So far, wormholes remain theoretical objects. We haven't observed them directly, and we lack the technology to create them even if we knew how. But that doesn't mean we've given up on finding evidence of their existence. Some physicists believe that we might be able to detect wormholes indirectly by observing their gravitational effects. Just like any massive object, a wormhole would warp the fabric of space-time around it. This warping could affect the path of light passing nearby, creating a gravitational lensing effect. By studying these lensing effects, we might be able to infer the presence of a wormhole, even if we can't see it directly. Other potential signatures of wormholes include unusual radiation patterns or gravitational waves emitted as objects travel through them. While the search for wormholes is still in its infancy, the development of new telescopes and gravitational wave detectors gives us hope that we might one day detect these elusive objects. And if we do, it would revolutionize our understanding of the universe and our place within it. Section 11. Conclusion: wormholes, fact, fiction, or the future of space travel. Wormholes remain one of the most intriguing and mind-boggling predictions of modern physics. These theoretical tunnels through space-time, if they exist, could unlock the secrets of the universe, allowing us to travel to distant stars, explore other dimensions, and perhaps even journey through time itself. While the challenges of stabilizing wormholes, finding exotic matter, and resolving the paradoxes of time travel are formidable, the potential rewards are too great to ignore. The study of wormholes pushes the boundaries of our understanding, forcing us to confront the deepest mysteries of the cosmos. Whether wormholes remain in the realm of science fiction or become the future of space travel, their exploration will undoubtedly continue to inspire our imaginations and drive our quest to unravel the secrets of the universe. For in the vastness of space and time, the possibilities, like the universe itself, may be infinite.